Hello and welcome to my first video in a while. It's been a while since I made a video. That's because I started my PhD in bioinformatics data science. And what I'm basically doing, at least for my first rotation project, is that I'm using machine learning to map amino acid sequence to a fitness value for enzymes. So maybe some amino acid sequence would have a certain activity associated with it in breaking down plastics possibly, or catalyzing a substrate. So that's what I'm doing so far. It's pretty interesting. But one of the ideas that I had was incorporating uncertainty into the models. And I'll show you the idea that I had. However, this idea didn't really actually make it to my project. It was just something that I proposed, but it was kind of just like denied because there's probably already tools out there that do this already, possibly. I'm not really sure, but that's what they said. So here's my idea. So recall that the goal of regression is to find the best fit for a set of data. But what if we take it a step further and include error bars for each prediction? That'll be pretty cool. If we had some errors for each prediction as a function of x, your model inputs. You can get error bars on your outputs. That could be useful in a lot of situations, I think. So there are two types of uncertainty that we will consider. The first is aleatoric, which is measures your deviation in your measured outputs from your predicted outputs due to measurement noise. And the second is your epistemic noise, or uncertainty, which is which measures the deviation in your measured outputs from your predicted outputs due to the model itself changing parameters. So for example, if you had a linear model in two-dimensional space, and imagine you have one point fixed, you have another point that can vary up and down. Well, depending on the position of that second point that varies, you will get different linear models with a different y-intercept and slope. So, and let's just say that you didn't have any noise in your outputs, then you would still have a deviation in your in the measured value and the predicted value due to this slope and y-intercept changing. So these are actually two independent sources of uncertainty, and that will be important for quantifying the total uncertainty. So first we will address aleatoric uncertainty through a custom loss function, and I'll guide you through the process. So a general regression model says that your ith output, y sub I, is equal to some function of your ith inputs, x sub I, parameterized by model parameters theta, plus your residual at I, which is the difference in your predicted and measured outputs. And for this purpose, we'll just assume that these residuals are chosen from a normal distribution with mean 0 and standard deviation. The standard deviation could actually be a function of your inputs. So we will assume heteroscedasticity instead of homoscedasticity, where homoscedasticity is where the standard deviation is constant, And heteroscedasticity means that the standard deviation can vary with your input. And we will parameterize this standard deviation function by gamma. So then we can say that's yi minus f of xi parameterized by theta is drawn from a normal distribution with mean 0 and standard deviation of as a function of gamma. And that's because if you solve for epsilon sub I, then you'll see that it's equal to y sub I minus f of x sub I parameterized by theta. And because y sub I minus f of x sub I parameterized by theta is chosen from this normal distribution, that means that the probability of y sub I minus f of x sub I parameterized by theta is equal to this distribution over here. Actually, I have an idea. How about I use this laser pointer? So this is the distribution, the normal distribution described up here. And this is actually equal to the probability density function, sorry, not probability function, but probability density function, p of y sub I given x sub I parameterized by theta and gamma, right? So you see the theta over here and the gamma over here in the equation. And the reason why it's p of y sub I given x sub I is because why is it that so? It's because x sub I. It's because you're given the inputs, but the outputs are what varies. Essentially, that's why I think. So now if we assume that all the y sub i's are independent, that means that the probability density function of all the y's given all the x's parameterized by theta and gamma is equal to the repeated multiplication, sorry, is equal to all the ith probability density functions multiplied together. So we want to choose the theta and gamma that maximizes the likelihood of all of our y's given all of our x's. So that is the theta hat, gamma hat arranged as a 2 by 1 matrix is equal to the argmax of theta gamma of this probability density function in that red box, which corresponds to this expression in that red box. So now we are going to derive the corresponding loss function to that maximization problem, or that maximum likelihood function. And first we're just going to, and the reason why we do this is because it makes it easier for us to solve using our current optimization tools. I think the field is called quadratic programming or convex something optimization. But anyway, we're just going to do something simple. We're going to just substitute that expression into that p of y given x. So what we're going to do here is that we're going to take the negative natural log of the expression on top, just a negative natural log. And since the natural log is a monotonically increasing function, then if we take the negative of it, then if we were previously maximizing the this expression, or then we will be maximizing the natural log of the expression, and then that corresponds to minimizing the negative of that natural log expression. And we still want to find the theta and gamma that minimize it. So then if we continue to simplify this negative natural log expression, then we get this expression over here. And we still want to minimize it, because that is the negative natural log. That's just another way of expressing that negative natural log right there. And let's just say that the number of examples we have ranges from 1 to n. That means that we're taking the sum from 1 to n instead of just the sum over all I. And we just take 1 over n because conceptually it's the we're minimizing the loss function per data point. The loss per data point. So if we want to get fancy, then we may add this ridge regularization term over here, which provides a penalty for higher values of theta and gamma. And what that does is that it makes the optimum theta and gamma, theta hat and gamma hat, less sensitive to noise. But we don't want to get too fancy here, so let's just stick with the previous expression, just to keep it simple. Here is our loss function. And within this loss function, you can see our aleatoric uncertainty function right there. So if we assume some form of this variance, this aleatoric variance, say that maybe we assume that the natural log of our aleatoric variance function as a function of x is linear, which they did in this paper called, I forget what the paper's name is, but it's by Kendall and Gull. I'm not going to worry too much about references here, but yeah, if we you can extract that aleatoric uncertainty as the sigma squared of x parametrized by our best gamma hat. So now that we have our aleatoric uncertainty in the form of a variance, we will now address our epistemic uncertainty. So we will find our epistemic uncertainty through a process called bootstrapping and aggregation, or bagging. And this procedure involves generating what are called bootstrap samples from the training data by sampling with replacements, then training a separate regression model on each of these bootstrap samples of size capital B, using our custom loss function, of course. That includes our aleatoric variance in there. From this bootstrap, we could obtain a set of functions that outputs our prediction as a function of x, f sub u of x, from which we can calculate the mean prediction function f bar of x. So our epistemic variance as a function of x would then be sigma squared epistemic of x is equal to 1 over b times the sum of all from b is equal to 1 to capital B of f sub b of x minus f bar of x squared. So the squared differences divided by the sample size. So now that we have expressions for epistemic and aleatoric uncertainties in the form of a variance as a function of input x, now the next step is to combine them into one single uncertainty. And then we can actually create a confidence interval from there. So if we assume that the variances are independent, then we can just sum them together, because that's one of the properties of variance that you can prove if you so choose. So we'll say that sigma squared total, which is our total variance, is equal to the epistemic plus the aleatoric variances. And that assumption that the variances are independent is a very good assumption, because as I described in the earlier slides, it's true. It's true that they're independent. So since the aleatoric noise followed a normal distribution, we assume that. And now we're going to assume that the distribution of model outputs in the bootstrap samples approximate a normal distribution. That means that since the aleatoric and epistemic variances were calculated under the assumption of a normal distribution, that means that the sum of them is assumed to be calculated from a normal distribution, sigma squared total. And that means that y of x, our observed output as a function of x, is drawn from a normal distribution with mean y hats of x and variance sigma squared total of x. So what I think this means is that you can say, for example, that like you're 95% certain that your measured values will fall within a certain range given a y hat. So if you imagine like if you have like a linear model, then like one of the points on that linear model line will be y hats. If you for a given x, you can find the y hats, model prediction, and around that model prediction will be a confidence interval. One providing an upper value, one providing a lower value for the measured value. You don't know the measured value yet, but you can predict your measured value. So that could be useful. And then you could also interpret this in such a way that if you know your model structure is correct, then you can say that maybe you're 95% certain that the true parameter falls within this confidence interval range given a measured output y. So if you imagine like for a given x you have a measured output y, you could construct a confidence interval around that measured output y, and you can say that maybe you're 95% certain that the true parameter, the true y value, y hat, falls within that range. So that is the end of this video. But I have one more thing to say, and that is an idea. So my idea actually came from that previous slide, thinking deeper about that subject of like why this could be useful. Say that the true model that best represents your data is a polynomial model of degree 2 in 2 dimensions, right? Just a simple 2-dimensional problem. And let's just say that you use instead to represent the data, you use a linear model with heteroscedastic noise, like we kind of like did in this presentation. We assume we assume that the noise is a function of x, or the variance is a function of x. So then what if you also know that the true model is not actually, the true noise is not actually heteroscedastic. The true noise is constant. Well, that would mean that you have the wrong model. That means that the model isn't linear, it must be something else. So what I'm saying is like, what if like you can kind of get that quadratic model from the information that you gained from that linear model with heteroscedastic noise. So that's a really interesting problem to consider. And I think it might involve like calculus of variations. I think it might involve that because like you can actually probably minimize a functional of least squares, an integral where y of x is actually what you want to minimize. So I'm actually working with ChatGPT, and I'm working with AI on this problem, and hopefully I can actually get something cool. And I don't know if they actually, if it's a thing in mathematics or not, but what if it's not? You know, I don't know. Um, but yeah, so I think my next video will be on calculus of variations and the Euler-Lagrange equation. That'll be pretty cool to like make a video about and understand. So see you in the next video.